Hey, good morning and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we like to do this webinar really for the members of our ZP Developer Zone and also for sort of technical questions that have come in during the week. So I will essentially jump straight into it and start off with, I'll very quickly go through the slide and just say, don't forget we have the ZP Academy. There's a couple of free courses on there. So there will be quite a lot of technical information today. Cyclic voltammetry, chronoamperometry will be mentioned. And if you're not familiar with these techniques, then you really need to take a look at the ZP Academy. There are two free courses on there that at least give a introduction to this material. And we have this webinar. So every Thursday, 8 a.m. I think unfailing in over a year, there's always been this webinar. Including delivering this webinar at midnight, for example, when out and about traveling. And we have our collaborations. We definitely have a couple of ZP Developer Zone members coming over this summer to do various placements with us. We offer jobs through the academy, through the Developer Zone, and we also have a dedicated website. I just want to say good morning to Aftab. Nice to see you, Aftab, this morning. And then we have workshops. So, for example, if you're going to Sigues, which is in Spain this weekend, there's a conference, Biosensors Congress Conference on Zimmer Peacock. It's organized by El Sevilla. The chair of it is a gentleman called Richard Luxton at UWE, University of West of England. And they've been kind enough to invite us to give a workshop. So we'll be giving a free workshop to the members of that. As I say, the ZP Academy, there's Introduction to Biosensors. That's a free course. So log on to the ZP Academy. It's a free course. And there's also Electrochemical Techniques for Biosensor Developers. That's also a free course as well. So we will talk about applications this morning. But really, to have the science behind it, you probably need to take a look at those courses. Now into the questions themselves for this week. So question number one, somebody wants to measure urine protein and the creatinine ratio. So how much, essentially protein is in the urine versus the creatinine in the urine. I think I just briefly looked into this. I've come across creatinine a lot in my career, and also the same with protein as well. I think this is due to sort of renal health. So that was question number one. Question number two was somebody wants to make a choline measurement, and we will discuss that. Question number three was really a detailed discussion on cyclic voltammetry. Cyclic voltammetry, people hold it in a very high esteem, and they consider that the shape and etc. is very important. But cyclic voltammetry, I think it's held in too high like say a light, and I'll discuss why it's the shape it is, and then in fact, it's interesting, but it's not in biosensor development. I think it's an interesting technique, but whether your cyclic voltammetry is let's say ideal or non-ideal, I think that's less important, but we will discuss that. And then question number four came in just last night. The inquirer was asking about our carbon 101 electrodes, and I want to contrast that with our carbon hypervalue electrode. So let me be quicker. We got four questions, quite a lot of information. So question number one was really about they want to measure the ratio of protein to creatinine in urine. So apparently, there's a ratio, and here I've called it albumin, but albumin is a kind of a ubiquitous or a common protein among the proteins, let's say. So albumin versus creatinine, what's that ratio? Now, if we were doing this with a commercial business, I would actually be developing a test like the one playing in the video at the moment. Now, I've done other videos about this, but if you're really going to do a medical diagnostic of the kind of quality that's sort of shown in the video, then this is a large commercial effort, and it really needs to be commercially sponsored with a kind of funding. Now, when it's more university or hospital university based, then you are better off going for technologies which are intrinsically lower cost. So here we have, an Android a USB potentiostat and a sensor in it there. Now, I know that when you're trying to measure protein versus creatinine ratio, or albumin versus creatinine ratio, I do know that it's going to require about 2 sensors to do this, and therefore I would actually split the project in 2 parts and do an albumin sensor with one, let's say, PhD or one master's or one postdoc, and then I would have another one working on creatinine. These two sensors can be brought together later on, but when you're asking the question how to measure the ratio of these two things in the urine, they have, I think from a project management perspective, these 2 sensors have to be split, or these 2 sensors have to be treated as little separate projects, with a scientist, like, let's say, on each one. It's not very hard to actually to create a sensor with essentially 2 working electrodes. This is a strip of electrodes that we sell on our website, and you can just get a pair of scissors and just cut 2 sensors off the end, for example, there. So the gating item is not creating a screen printed electrode with 2 working electrodes. We can do that today. It's really functionalizing these electrodes to be specific to albumin and creatinine, and then making the ratio can happen in the software. So the ratio itself is not so hard. It's actually making the 2 sensors. So let's dive into the albumin. I did obviously, a very quick search, electrochemical detection of albumin. And one of the first hits I got was quite a detailed, I would almost call it sort of master's thesis on using MIPS, molecular imprinted polymers. At ZP, we've used MIPS quite a bit in our time, so it looked fairly credible. I did notice that they got their signal using sometimes EIS, electrochemical impedance spectroscopy, and I also noticed that they were also using differential pulse voltammetry, DPV. Many of the potentiostats now, Zimmer Peacock has an Anapot EIS, Zimmer Peacock has an Anapot. We also sell the Sensit Smart. Many of these potentiostats can do DPV, for example. So you have to pay a bit more for EIS, but DPV is quite readily available. In fact, Zimmer Peacock, we do I think a Sensit Smart plus 1,000 electrodes for less than €1,000. So maybe that will be the way to go about it. And I hear that the Sensit Smart actually allows you to do EIS as well. We do own them. I've just not tried the EIS function on them at the moment. But back to it. Albumin looks very readily, or it looks, at least from the literature, very doable. This was a very detailed article that I found, and it was free. So that's the wonderful thing about electrochemistry. There's always plenty of literature material about this. I'm very boring. I would obviously recommend the hypervalue electrode. We use this, day in, day out in our business. Now, question number 2 is creatinine. So with creatinine, obviously, I've done some literature searching just quickly on this. That you can have creatinine, and if you have I would call it an enzyme cascade of creatinine amidohydrolase, creatine amidohydrolase, and this sarcosine oxidase. You can end up, again, I would do it on the hypervalue electrode, you can end up using this cascade of enzymes with hydrogen peroxide. And I think many of you won't say, oh, this is too complicated. It actually struck me that it was fairly similar to a purine sensor that we do commercially produce at Zimmer and Peacock, where we have, we call it the purine sensor, and we detect a whole, let's say, series of purines. But we do have a cascade of 3 enzymes before we actually generate the detectable hydrogen peroxide. So the albumin can be done by the previous slide I was showing, and I think the creatinine, it will take some more work because you essentially have to immobilize these 3 enzymes onto the electrodes, and then you would just have what we call an enzyme cascade. Once you're ending with hydrogen peroxide, then you're sort of becoming, this is a molecule that we talk about a lot in the ZP developer zone, and this is an electrochemically active molecule. I'm going to leave this one now because I'm always conscious of time, but the question was, can we measure protein and creatinine in the urine? And the answer is yes. Treat it as 2 separate projects, I would say. Um, it's not straightforward, you know, it will take several months to do that. So to do a proof of principle will take several months, let's say. Now, question number two is this group is trying to they're trying to repurpose a glucose strip to be a choline sensor, and they use a glucometer for a readout. So there's either build the choline strip from essentially ground up or try to repurpose a glucose strip. I will discuss both things. First thing, this I think the simpler route is actually just to build yourself a choline strip. Um, the only unknown is I know there's a choline oxidase. I haven't looked for the availability. I want to say hi to Abukar. Thank you for joining this morning. The one thing I haven't looked into is the availability of choline oxidase. Maybe I should have, but I did notice there was a choline oxidase. And because there's a choline oxidase, and as long as you can get hold of it, that's a big as long as you can. The reason being as well is a lot of enzymes and macromolecules, you know, they are um, rightly fabricated in China these days. And so actually some of the lockdowns in China are causing some supply chain issues, not only in the electronics industry, but also in the sort of biotechnology industry. So I hope the choline oxidase is available. Just be aware that actually there is if it's coming in from China, you might have to expect some delays, and there's not much you can do about it in this moment. Let me describe a generation 1 and a generation 2 choline sensor. I have exactly the same slide, and Aftab, who's here this morning, will have seen this slide lots, but today we're going to talk about choline oxidase. So take your electrode, functionalize it with a mediator. This inquirer, when they asked about this, they said, oh, well, we only use like ferricyanide. So I will touch upon ferricyanide being the mediator for this. You need to have your enzyme entrapped within a polymer. You can just drop coat it on. I suspect that will work as well. You may not need this barrier layer. Whether you need a barrier layer or not really depends on the um, clinical range of the choline and the enzyme activity. If the enzyme activity is high, then you don't need to limit the amount of choline reaching the sensor. If the enzyme activity is low and the clinical concentration of choline is high, then you will need to limit the amount of choline reaching the sensor. So let me dig into this a little bit deeper. So I got a feeling that you've functionalized the electrode. You've put some choline on there. In this case, I've got a barrier layer in it. I would almost try it without a barrier layer to start with. The choline oxidase converts choline into betaine. That happens in the. I should have put choline there rather than betaine. But what's happening in the enzyme layer here is choline is reacting with the choline oxidase. Choline oxidase becomes reduced. Choline becomes betaine, and oxygen is reduced to hydroperoxide. At which point then the hydroperoxide can be detected. The person inquiring earlier on about their creatinine sensor also needs to watch this as well. See the way that hydroperoxide is produced, and then we can detect hydroperoxide using a mediator. I've showed the mediator here in its reduced form. It gets oxidized and then it gets recycled by the electrode. By the way, you don't have to formally have the mediator in its reduced form. So you could put ferricyanide on there. When you apply a negative voltage to ferricyanide, it'll become ferrocyanide anyway. So you can generate the mediator in situ. But this is a high level way on how you would make a choline sensor. You know, I would, if I was doing this work, I might have, I might deposited choline on the electrode, sorry, choline oxidase on the electrode. I might have deposited some ferricyanide on the electrode, and I just give it a go, to be honest with you. Lo and behold, it might even work. I suspect it would work. You can get more sophisticated, and you know, maybe I'll describe that a little bit now. But as I say, if you apply a sort of negative voltage, I assume something like minus 200 millivolts, but I'd have to do some real lab work to sort of tell you really what that voltage would be. In another lecture, I could even show you what I think the signal will look like, but today's I haven't. I would call that, because you're using a mediator, I'd always call that a generation 2 choline sensor. If you were using something like platinum or gold electrode, you could actually just go for a simpler electrode and just use With platinum and gold, you can detect the hydroperoxide directly, and I call that a generation 1 sensor. There you would use that magic number 650 millivolts to detect the hydroperoxide. I think in this case, what would I suggest? I would suggest probably going for starting with the generation 1 and then maybe progressing it to the generation 2. Problem with the generation 1 is you need either a gold or a platinum electrode, which makes it more expensive. If you just go straight to the generation 2 sensor, you just need a carbon electrode and ferricyanide. So if you're experienced with ferricyanide and carbon electrodes, maybe just skip the generation 1 and go straight to the generation 2. Comments on mediator. So I said this also applies to the creatinine sensor. I showed you a cascade of an enzyme cascade where it finished with hydrogen peroxide. That both for the choline detection and the creatinine earlier on, they finished with hydrogen peroxide. Hydrogen peroxide will react with, for example, ferrocyanide. The ferrocyanides can be generated in situ from the ferricyanides. Ferro becomes ferricyanide, and hydroperoxide is regenerated to oxygen. And we can essentially keep on recycling the ferricyanide, and it's really the rate at which this electron transfer and I should have put this Fe2 plus here. The rate at which we generate that is linked to the amount of hydrogen peroxide. So that really is the source of our signal. So very different analytes. Let's say, we've talked about creatinine this morning and choline this morning, but you can essentially use so both of them use oxidase enzymes, both of them use hydrogen peroxide, and you can then mediate that hydrogen peroxide using something like a ferricyanide mediator. Now they might want to actually repurpose a glucose strip. So what I've shown here, this is a glucose strip. I feel like the inquirer already knows this, but when you look at a glucose strip and you see this yellow color, I used to think that this yellow color was glucose oxidase, because glucose oxidase in solution is yellow. I realize these days it might actually be the ferricyanide that is producing that yellow color because it's in higher concentration, but maybe a bit of both. But many commercial glucose strips do have ferricyanide, and they have glucose oxidase on them and ferricyanide on them. So this inquirer is asking, I want to repurpose a glucose strip. I think to be honest with you, rather than trying to repurpose a glucose strip and use a glucose meter, I suppose I should say, the series of chemistry that I think is on there is there's glucose oxidase on there and some ferricyanide on there. And we have discussed that this morning. If you want to repurpose a glucose strip, you could try wicking in some choline oxidase solution and just letting it dry back in the strip. In theory, it should work, but in practice, a glucose meter that you can buy from Walgreens or CVS, it has a very specific expectations. It expects a certain current at a certain time, and once you start, let's say, modifying the electrodes, it's not going to behave the same way, and the meter's going to pick up on this, and it's actually going to throw an error. So if you want to buy a commercial glucose meter and a glucose strip and actually add your own choline oxidase enzyme into it and try it, sure, give it a go. But don't be super shocked if it actually throws an error. I think you're in a better position where you actually just have to unfortunately build your own choline strip essentially, in the ways that I've described this morning, where you replace the old glucose oxidase with choline oxidase, and I think it should work. So you are very welcome to obviously try modifying a glucose strip and trying to use even the glucose meter that comes with that strip. But these glucose meters, the manufacturers set them up so they have a very definite way of working. And when you start interfering with the solutions on board, it will detect that, think there's been a manufacturing error or some sort of sample error and throw an error, and you won't get a result. But that said, you can always try it, of course. It's not that hard to try it. Cyclic voltammetry, I'm going to talk a bit faster this morning. It's 8:20 now. So people hold cyclic voltammetry and expect a very certain way that cyclic voltammetry should look. Here's the, rather usefully actually, I realize I'm using the cyclic voltammetry of ferricyanide, which is kind of useful actually, because I realize I mentioned minus 250 millivolts earlier on. And that's because it's well negative of the reduction peak from ferri to ferrocyanide. So here's the cyclic voltammetry. Obviously current versus voltage. If you're not sure about this, have a look at the ZP Academy. I just saw a question come in. Somebody's asking how long our pH electrodes could stay active when deployed in soil. So we do sell a solid. This is just a question that came in on YouTube. I do try to answer these as we go along. So ZP sells a solid state pH electrode. We have a hypervalue pH electrode. They're really quite cheap. The nitrate equivalent that we've got runs for 6 months. I've never run the pH sensor for a long time in soil. You might actually find it works for 6 months, but you'll have to give it a go. We haven't had a go of that. So this is the cyclic voltammetry of ferrocyanide. I know I've written ferricyanide here, but on a hypervalue electrode. So we're oxidizing the ferro to ferri, and we're reducing the ferri back to ferrocyanide. Now, what we're doing in this is the waveform. Many of you will have seen the waveform in the past, but we go from 1 voltage up to a new voltage and back again. So that's a triangular waveform. And we have a starting voltage. In this case, the starting voltage is about minus 500 millivolts. And we go to a sort of second voltage of about plus 500 millivolts, and we cycle back again. So that's the waveform. It's harder to explain than it is to actually do this experiment. This experiment is like a 2-minute experiment. It's not hard. You just put the sensor or the electrodes in the front of the potentiostat and put a drop of, this is the anapot and this is the hypervalue electrode, and you just put a drop of something like 5 millimolar. Ferricyanide is fine to do this in about 1 molar KCl, and it should work perfectly fine. It just happens to be what we call an E reaction, because it's just a 1 electron transfer and back and forth. I realize that that's in the way. I will go a bit quicker now. Let's just explain the shape of these cyclic voltammograms a little bit more. So this is the CV that we're just looking at. There's several regions in this CV. The first region that we have, and I've labeled it up here, is the capacitive or the background signal. In an ideal world, the current is essentially 0, but there's what's called a capacitive charging, so it's not quite sitting on 0 current, but we really have the background signal here. Then we have a region which we call the Faradaic region. I think the Faradaic region is not really that good a name. I mean, it comes from Faraday, one of the sort of, founding fathers of electrochemistry, but it's not very explanatory in itself. But they call it the Faradaic, let's say, current. And it's really because when you actually got electrochemistry going on, you kind of they call that Faradaic. So the reduction of ferricyanide to ferrocyanide, that's a Faradaic process, or the reverse oxidation is a Faradaic process. So we have a background region on the cyclic voltammogram, and then we have this Faradaic current where we come up to a peak. Now in the foothills of this, down here, we have a sort of current that increases exponentially. So this is one of the regions I want to discuss. In this region, the current that you see is proportional to the voltage that you apply. So the current is proportional to the voltage, or so I should say the potential, the units of voltage, but the potential that you apply here. And there's an exponential term in it. And so you can almost see it in this simulation that there's an exponential rise, and the equation, does the reality reflect the equation, or does the equation reflect reality? But an equation that simulates this quite well is the Tafel equation. We should call this region the kinetic control, because it says that the current is under kinetic control, and that's electron kinetic control, and that kinetics is governed by the potential. And if I was to look at the concentration of the analyte, I would see that in the bulk it was 5 millimolar, and because we're in the electron transfer region, there's hardly any change at the electrode surface. But as we start going in, increasing the voltage, we come into an area that we call the mixed control, at which point then there's a slight drop in the concentration of in this case, the ferrocyanide. So now we have two processes controlling our current. We have the electron transfer, which I discussed as the Tafel equation, And now you start having, in this case, diffusion control. Diffusion is a form of mass transport, but it's diffusional control because it's not just the electron kinetics, that electron transfer kinetics that are governing the current, but it's also this diffusion that we're actually depleting ferrocyanide near the electrodes, and we're building a what we call a depletion zone. And the more voltage we apply, so as the more ferrocyanide we're depleting, until we get to a point where actually the ferrocyanide at the surface of the electrode has actually gone to zero. So the kinetics are going just about as fast as you possibly can. And there is, at this point now, the current is completely governed by the rate at which diffusion, in this case, is able to bring more ferrocyanide in. And we get to the peak current. And electrochemists think this is really important. I think they hold it in too high regard. But when you then have this other extreme, then you're using what's called the Randall-Sevik equation that says that this peak current is proportional to concentration, good, because that means we can make a biosensor from it, or a sensor from it. But it's also proportional to the, strictly speaking, the square root of scan rate. I'll explain that in a minute. But what you see here is you have a sort of diffusion is in this equation, and that's because at one point now, diffusion is the process that's governing the rate at which this concentration can arrive, and therefore the current that we're actually seeing. So cyclic voltammetry has a definite shape. I think people, think it's very important that it has this shape. Whether it's important or not, from a biosensor perspective, it's more like, as long as your signal is proportional to concentration, that's what's important. Whether you have an ideal shape is not necessarily so important. But I do now want to explain why, if you read any electrochemical paper, they often have, my current was proportional to the square root of my scan rate. Where does this actually come from? So I'll try and explain that now. I'm speaking rather quickly because of obviously the time. Now in voltammetry, either cyclic voltammetry or linear sweep voltammetry, we're going from, one voltage to another voltage, and as we go along, so we have different regions. So here I might be in my background region. At this voltage, I might be in my kinetic control region. At this voltage, I might be in my mixed control region, where I'm controlled both by electron transfer and by diffusion. And then once I get to near the peak, I'm really in my diffusion or mass transport control region. So these different regions give you these, gives you this distinctive shape, let's say. Now, the time at which it takes you to go from V1 to V2 ends up driving the peak height. I know electrochemists know this, but I'm not always sure that they know why it's like this. So this is I'll give you my explanation. So as you decrease the time, in other words, the scan rate increases. So as the scan rate increases, you will know, because it's, that actually the peak height increases. Now, the reason this happens is because we have a, in our, let's say, diffusion control region, we have a concentration gradient, in this case of ferrocyanide, which is proportional to the scan rate. So when we scan very fast, what this means is when you scan very fast, you go from voltage 1 to voltage 2 very quickly. You do it so quickly that, in fact, you have hardly any time to convert ferrocyanide, for example, to ferricyanide, and you get a very steep concentration gradient. Now, if you go slowly, it means that at each voltage, you're there for quite some time. It means you pass quite some current, and therefore you end up converting ferrocyanide to ferricyanide, and we get what's called an increased depletion zone. And so the faster we go, this distance that defines the depletion zone is shorter, and the slower we go, the longer it is. So when you ask the question, why is the peak height of my CV proportional to scan rate, it's because of the gradient in this diffusion gradient here. And this gradient, I can do a crude calculation on it and say the concentration difference, I've got a concentration difference of 5 millimolar minus 0 millimolar, because I'm assuming it's 0 down here, divided by the distance. So the distance, if I do a slow scan, is essentially a big number, and if I do a fast scan, the distance is a small number. And so when I have a small number, this because it's a reciprocal, I'll give me a higher current, and when the distance is larger, i.e. I scan slower, I have a larger D, and therefore this reciprocal, or because it's a reciprocal, I'll have a smaller number. And that is why in this equation, the Randall-Sevix equation, current is proportional to scan rate. The faster you scan, the steeper this gradient, and therefore the higher the current. And that's the root cause of it. Now, electrochemists really think this is super important, and I think it's super interesting, let's say, but it's not the make or break on making a biosensor. And I also want to sort of put it in context that they do hold cyclic voltammetry very importantly. I mean, there's another form of voltammetry called hydrodynamic voltammetry. And hydrodynamic voltammetry, I've just explained the shape of this CV. In hydrodynamic voltammetry, you use a rotating disc electrode. And I'm not suggesting everyone goes out and gets a rotating disc electrode. I actually think it can be a distraction to a biosensor developer. I did my PhD using rotating disc electrodes. I've owned rotating disc electrodes. I just don't think it's important for biosensor developers. But the reason I bring it up is because in a rotating disc electrode, if you otherwise did the same experiment of doing a voltage sweep, i.e. voltammetry, but you now rotate the electrodes, you are forcing material to the electrode and you get a very different shape. So let me give you an example of that. If you rotate this electrode quite low at 100 revolutions per minute, you get a voltammogram that looks a bit like what we've been looking at. That you have a baseline region, it comes up to a peak, and then it starts sort of depleting here. So at slow scan rate, it looks like slow rotation rate, it looks like a normal CV, or quite like a normal CV. And then the faster you rotate, the greater the current. So you can see that the current is increasing as they increase the rotation rate. And so it says to me, why is cyclic voltammetry so important? And it's not really so important because you could actually do using the otherwise similar excitation protocol, but you decided to change the mass transport. You don't get the classical sort of cyclic voltammetry now. You get hydrodynamic voltammetry. So I'm just sort of saying, don't overplay the importance of beautiful cyclic voltammetry. I could do the experiment in a different way, get a very different looking result, but it's not the thing blocking me from making a biosensor. Question number 4. I'm looking at the time, it's 8:32 here, so I need to go a bit faster. Question number 4. So people do inquire about our carbon 101 electrode. So this is our carbon 101 electrode. I've got lots of critiques on this carbon 101 electrode. It's one of the first electrodes we made, and I'm going to critique it. One of my first critiques is it's 30 millimeters long and 10 millimeters wide. So critique number 1, it's too big. Now it might feel nice in the lab, but at Zimmer and Peacock, our whole raison d'etre, the whole reason that I do this webinar is to help people try to make commercial products. Such large electrodes are not compatible with the whole philosophy of making commercial electrodes. It's too big, and I'll discuss that in a second. People do like it because you can essentially pipette onto these circles and pretty quickly, functionalize it. So I understand it's easy to use in an R&D setting. Problem is, if your perspective is just R&D and you're not thinking about the commercial perspectives, then you're going to run into a bit of a roadblock. So at Zimmer and Peacock, I much more prefer people to use our hypervalue carbon electrode. It's smaller, which gives us essentially lower cost of manufacture per piece. It's exactly the same connectors here. So here you have a 3 connectors. They're 2.54 millimeters separated, and you've got exactly the same thing here, 2.54 millimeters connect. That is important because it has become a bit of a standard now in the screen printed electrode world. Let's say that Drop Sense use it, the Palm Sense potentiostats have this connector. Everyone's kind of recognized this is a good standard in which to lay out the connector pads. Now the 101s that we make are made on ceramic. Ceramic is both an expensive material, and also it's a material that actually has a ceramic wafer is about 100 millimeters long and 100 millimeters wide. So it's quite a small piece, which limits our, let's say, manufacturing density. Whereas we can get what's called roll-to-roll manufacturing for this kind of polymer material. So that's made of ceramic. It means you can't do roll-to-roll or reel-to-reel. This is polymer. You can manufacture at a much lower volume. I just want to say hi to Hitcham. Nice to see you, Hitcham. So the polymer is easier to manufacture. We can do it reel to reel. We can get the prices right down. So the ceramic, for example, I mean, in order to get a reasonable price on the ceramic, we have to sell it in blocks of 3,000 electrodes. And then we can get it down to just over €2. And because the euro is now equivalent to very equivalent to the dollar, let's say $2. So I sell the 101 carbons. I understand people like it in the research community, but I always encourage people onto the hypervalue electrode. The reason being is if we sold an unsingulated sheet, and by the way, you can just cut these sheets with scissors, but if we sold it unsingulated, we can sell it for less than 50 cents each, and that's only for 300 electrodes. So it's just almost orders of magnitude less expensive. Now, the reason that we're trying to make this hypervalue electrode is so low cost is because I think Zimmer people were quite unusual that I do have a background in high volume manufacturing of biosensors, and I know that a glucose strip would have something like 2 to 5 cents per cost. So I know that that's the kind of price point that people want to get to. You can't do it on ceramic, but these polymer electrodes, we can get there. So a sheet of 300 that you can cut with scissors is less than 50 cents each. To functionalize it's not that hard. You can just use a pipette tip and you can just functionalize it like that. And we do hand functionalize these things. And this is an example here of something like 3, 6, 9, 12 data points, 4 concentrations, all tested in triplicates. And we were able to get good repeatability and essentially good linearity. So have no fear about how to functionalize this electrode. This electrode looks much more like a glucose strip. This is one that we've converted in with microfluidics, and that's important now because I do think that people need to think about the microfluidics. If they're looking for an electrode, they're often going to have microfluidics associated with it. In this channel, the microfluidics, the way the solution would run onto this, you would have a reference electrode, then the working, and then the counter. It means that the solution, as it flows on, it essentially shorts the electrodes together, and that can be the signal to start the assay. So obviously with a glucose sensor, you put a drop of blood onto a glucose strip and it just starts because of this layout of geometry. That's not how the 101s will work. They don't have this, they have no thought about how the sample's going to come to the sensor and how the assay's immediately going to start. At ZP, we are generally thinking about that. Just play this video very quickly. In this video, we're just showing you that, in fact, we have changed this SPE into a microfluidic device, and you can see the way that the sample wicks on. And it's that wicking on that's why the electrodes are the way they are. And also, it's a similar thing. If you're trying to make wearable sensors, I would encourage you to use our hypervalue carbon electrode because it's flexible. A, it has the right geometry to be in a flow channel, and B, it's flexible. So it can be sort of squashed and squeezed onto the skin. So people are very welcome to obviously, to get hold of the 101 carbons, but I would genuinely say, just skip straight ahead, go on to something that's much more commercially realistic, which is our hypervalue carbon electrodes. Right, so the time is 8:38. I need to be quick. So question number 1. Yes, it's going to be some effort, but you can measure urine protein and creatinine protein using electrochemistry. Question number 2. Yeah, I'm pretty sure you can measure choline. Maybe the biggest risk on measuring choline at the moment is getting hold of the oxidase. I haven't looked into the enzymes availability. Super detailed discussion on cyclic voltammetry at the moment. I just do it because I want to sort of explain to you why the shape is the way it is. And also say, the shape is the way it is because of the way you often do the experiment. If you did the same experiment but you rotated the electrode, you get a different shape. So why is the shape quite so important as people think? The answer is it's not quite so important as people think. If your signals versus the concentration for a biosensor developer, that's much more important. Question number 4, carbon electrodes. We do make the carbon 101 available. Just to get a reasonable price point, we actually have to put it into pack sizes of 3,000. And honestly, you can get a pack size of our hypervalue electrodes, or 300 electrodes, for less than 50 cents each. I mean, that's much more economic, and it's much more of a platform that I believe that you can commercialize. So I just want to say thanks to Hitcham, Abu Duka. I do appreciate the question on pH sensing. I feel I've been talking non-stop for almost 40 minutes now. So thank you very much for attending. Any questions, drop them, to ZP. As you can see, we try to give detailed answers, and we appreciate your attention this morning. So I just want to say thank you to everyone online. Thanks particularly to Aftab, always here, so appreciate it. All right, take care. Have a good day. We will do the webinar or the vlog on Sunday at 8 a.m. London time. No need to watch it live. It's also recorded. And there is if you're attending the Biosensors Congress this Sunday in Sigues, Zimmer Peacock's doing a workshop from 2 p.m. to 5 p.m. and that's in Spain. All right, take care and thank you very much.